I'd like to welcome you to our first AES Standards webinar. I am Bruce Olson, Chair of the AES Standards Committee. Here's a short introduction to the AES Standards Committee. Why do we have AES standards? The business of audio professionals is to supply audio services and to produce the equipment that supports them. Real-world audio systems use components from different manufacturers, and the interface between these components needs to work predictably and reliably. AES standards help to define interoperability between audio systems components and support the businesses that use them. AES standards are respected throughout the audio community. We have a number of AES standards committees focused on digital audio, preservation and restoration of audio recording, a subcommittee on acoustics, and a subcommittee on interconnections. I'd like to now introduce Merlin Van Veen and Roger Swanke. They are the co-chairs of the SC-04-03-A task group that is developing a procedure for loudspeaker test and measurement using music simulation test signal called M-Noise. Go ahead, Merlin.
Thank you, Bruce. So I'm going to share my screen as well, and then we're going to hopefully get into something which has become very dear to us. Almost there. Okay, is my screen visible?
Yes.
Excellent. So as Bruce said, we're going to talk about loudspeaker test and measurement using noise in this case. But before doing so, please welcome my fellow co-chair, Roger Schwenke, senior scientist at Meyersound. We already heard his voice. Pleasure having you here, Roger. And I am Merlin Van Veen, senior technical support and education specialist at Meyersound as well. I've been asked to do some household notes, which is there is the option for you to do questioning, question and answer. In the bottom of your Zoom interface, there's a button, a balloon icon, which has Q&A next to it. That is where you can populate your questions, and then we will be happy to answer those to the best of our abilities at the end of this presentation. So as Bruce mentioned, we've been approached as chairs of the SC-04-03-A task group. Roger and I chair this task group, and we're involved in developing a standard known as Project ID X250, measuring maximum linear peak SPL using noise. And this series of webinars is to grow the awareness of standard development, the work that goes into standard development, raise more traction, raise more awareness, gain more traction for standard development. So hopefully this will be the first of many exciting webinars on the topic. Before we continue, we'd like to acknowledge several people, starting with Colleen Harper, who reached out to us together with Bruce Olson, the Standards Committee Chair, if we were amenable to doing this, and we're very grateful for that. Also goes for fellow task group member Richard Cabot, who has been a very dependable task group member. Great deal of knowledge and helps us expedite the process. Same goes to Steve Hutt, which is the chair of the parent committee that we report to, the SC-04-03 parent committee. But I also would like to take my hat off, a big shout out to our own task group members, which are currently over 70 people. And we meet every 2 weeks over Zoom, and I think it really deserves a shout out that this has been going on, even though we're in the middle of a pandemic. So many of these people are volunteering, and I just want to take a moment to acknowledge them, take off our hat for those people that join us every 2 weeks. By today, or by this week, we've had over 25 meetings, and we're making very good progress as we're about to discover. And on that note, I'm going to hand it over to my co-chair, Roger.
So yeah, we'd like to acknowledge John and Helen Meyer as well. They had the vision of, developing a signal and this procedure, which we knew from the start we would have to make freely available in order for it to be successful, in order for it to be widely adopted. And John in particular decided we really need a signal that's more like real content, and that we should develop time and resources to make it happen. And now here we are. So we can go ahead. I'll be asking Merlin to change the slides, and he can also use his judgment because we've been working on this together for quite a while. So in 2018, we made some videos about M-Noise and the procedure, and you'll see in a little bit where to go get them. Those are still available. And then in 2019, we made a website, mnoise.org. Because we wanted to make it freely available, we wanted to put some distance between Meyer sound and the signal and the procedures to help it gain acceptance. So there's a website specifically for it, and that's where you can find the videos I just talked about. And then in 2019, we started discussions about can we make this a standard and go through a community process and get really develop a consensus in the industry, which is always how I hoped it would go. I find that to be a pretty successful approach to standards. Is you write a paper first and say this is the idea, and then you see if people are willing to gather around it and refine it. As opposed to getting together people first and then trying to make an idea is, I think, a longer path usually. So Merlin published a paper that we'll give you a little summary of in October at the AES in New York, virtually. And I published a paper in SMPTE on the analysis that led to the signal. And more recently, we did a paper at the Institute of Acoustics on focusing more on coherence, what you can do with coherence. We'll talk about that more in this presentation. And so, we're talking about it widely. We want broad acceptance of this, and we're here at the AES to make it a consensus standard. So you can move on to the next slide. Here's our webpage, m-noise.org. And if you scroll down, there's lots of other things. If we go to the next slide, we'll see some little icons of the various videos. And now we can move on to the next slide. And yes. So this is my conceptualization of things is that we have a certain relationship to the lighting community, and sometimes it's positive and sometimes it's negative, and in this case, I kind of envy them in that I've never really wondered if a particular light bulb is going to work with a particular light fixture. It always seems to be straightforward. And if we go to the next slide, we'll see that they even have some lighting fixtures have little knobs, like we have in audio. It's kind of like a volume knob, and I've never worried about turning this knob up so far that I might burn out the light bulb. And it's similarly with the TV, like there's a brightness setting on the TV. I've never thought, I better not turn the brightness up for this particular TV show. It might burn out my TV, but it's okay to turn up the brightness for other TVs. It's not a thought that ever even occurs to us. So now if we look at the next slide, we'll see a different knob. Well, I have worried about this knob. I've listened to a rock or pop radio station, and I've been hesitant to turn this knob all the way up. Maybe my speakers aren't going to handle it. Whereas for a classical music station, I might turn it up with some confidence, but I would certainly never crank it all the way up until it stops, like I would with a lighting dimmer. So why is in our community there's some ambiguity about what the capacity of our speakers are, and so we're hesitant and nervous about using our loudspeakers to their maximum capacity. So what can we do? And we're also, what size, when you're buying components, what size amplifier should you use with what size loudspeakers? And there's some ambiguity in ratings and sort of a lack of confidence. And so what can we do to give people the kind of confidence that they have with light bulbs, to give the kind of confidence people have with other ratings, which you have on the next slide, such as weight. So like we hardly ever think about, this weight that's on the spec sheet, is that really true? It doesn't cross your mind because it's so easy to check, right? I mean, you can easily check if something is that weight. And if somebody, tried to be tricky with that number on their spec sheet, they would very easily get caught. Anybody could easily independently verify that number. And if that got out that that number was inaccurate, that'd be kind of embarrassing. So that was our goal with M-Noise, and the procedure is to have something that was straightforward and independently verifiable, so that you could put, this is the max SPL according to this standard, and people could have confidence in it and know what it meant. And most likely you wouldn't have to check it because everybody knows that you can easily check it. So, hopefully we could have an SPL number, that you could have confidence in the way that we have confidence in weight, or the way that we have confidence in the wattage of a light bulb. So let's think about the signals we've used in the past. There's a lot of history of using pink noise, and there's definitely merits to pink noise and some conveniences, but it's not like music. It varies quite a bit more, and it also, when you look at, so this is a band spectrum, we're looking at RMS levels. The RMS levels tend to roll off with frequencies compared to pink noise. And if we move on, we'll see that people have tried to model this music, or you can maybe briefly think about choosing a particular piece of music to standardize as your test, but that's not a standard process that I was getting people together to make that choice. Maybe someone else could do that. That's more of a challenge than I'm up for. So there's this other aspect of signals that we'll talk about quite a bit, which is crest factor, which is not just the average level, not just the average level as a function of frequency, but the peak level, and the peak level as a function of frequency. And so there's a history with pink noise of letting the peak level be what it is versus manipulating it to be different. And we'll see that at the top bar here, you see the average level with the long green line is one level, and the peak levels are about 12 dB above that. And that's relatively consistent whether you low pass pink noise or your high pass pink noise. It has about this 12 dB crest factor, and that's a little bit counterintuitive. One would expect, you need high frequencies to make a sharp square wave, or to make a really fast peak, you need high frequencies. So wouldn't the high frequencies have a higher crest factor? And they do a little bit when you analyze pink noise in bands. It's maybe down a dB from 12 dB crest factor at the low frequencies, and it's up about a dB in the high frequencies, but that's really the same as saying it's flat plus or minus a dB. So pink noise has this very consistent crest factor as a function of frequency, yet if we high pass music, which is about to happen on the screen, we find that the crest factor in musical signals is much higher at high frequencies. It's more like our intuition that the crest factor should go up with frequency. So that's not a signal that has occurred before. We can move on to the next slide. That's something different, and we wanted a new test signal that would represent that difference somehow. And so the paper we published in SMPTE talks about the derivation of the signal. We analyzed a large amount of content and looked at the crest factor in octave bands. So Merlin has very generously gone and made little QR codes for quite a lot of the slides in this presentation. So this QR code will take you to this paper, and if we go to the next slide, there is a YouTube, like this presentation, there's a YouTube of the SMPTE presentation. So these papers that we've published, we're just going to give you a little taste of them, tell you, describe the topic that's covered in these papers, so you can judge whether you're interested in looking into them further or not. So let's move on and look at these various other simulated program music is the term that's often used. And they generally have a high pass and a low pass, and there's some rate at which the sound increases at high frequency, and that and M noise is different, but not terribly different in that regard. But this is just the RMS level, and all these other signals are really filtered pink noise, so they continue to have the same crest factor as a function of frequency as pink noise does. So if we move on, we'll see an analysis of both peak levels and RMS levels. So see on the left here, all those gray lines are entire songs that have been analyzed to find their statistics in octave bands. And we find that the peak level is relatively constant with frequency. And you'll see there's a pink line there that has pink noise, and pink noise has, as we would expect, a peak level, which is relatively constant with frequency. But then if we look at the RMS levels, we see that the RMS levels roll off with frequency, like we saw in our animations earlier in this presentation. And other simulated program signals have that characteristic. They have the RMS level, which rolls off, which pink noise does not. So what our goal here was with M noise was to sort of have a best of all worlds, was to have an RMS level which rolls off with frequency, like simulated program noise, but to have a peak level which is relatively constant with frequency, like pink noise. So those two things, were right. The peak levels and pink noise have always been a good approximation of what's going on, and the RMS level of simulated program noises has also been true. So that our goal here is to get both of those things to happen in the same signal. And so on the right, you'll see these black lines represent the crest factor of entire songs from a very wide variety of genre and decades. And in the paper, you'll see a long list of different styles and types of music. And every single one, without exception, the crest factor rises with frequency. And so the blue line there, that is M noise. That's how the crest factor changes with frequency. And that is what's different about it from test signals that have existed in the past. So let's move on. I think this will be about another paper presented at the Institute of Acoustics. So that was the signal that I just showed. Now there's also a procedure. There's a certain way of using M noise to determine the max SPL of a speaker. And you look at the transfer function, and you look at not just the magnitude of the transfer function, but also the coherence. And we'll talk a bit more about coherence in various slides. It's a very useful metric to help you judge the quality of your data. And one thing it can do is it can be an indicator of distortion. So we can see if a loudspeaker sensitivity is changing, its frequency response is changing, that's a form of nonlinearity, and we can also see if there's distortion with the coherence. And so let's move on, and we'll see what other things distortion can do. So I'm sorry, coherence can do. So usually coherence has a separate scale on the right. It's scaled in percentage. And here, if you imagine you're trying to measure a loudspeaker and somebody comes in and runs their vacuum cleaner, the noise that the vacuum cleaner makes is not at the input of your speaker, and therefore it's corrupting your measurement. And therefore, I have in fact had this happen to me. I'm scheduled to show up and measure loudspeakers, and so is the cleaning crew. And coherence will show you that. Coherence will show you that there is a signal at your microphone which is not caused by the signal at your loudspeaker. So let's move on. And this it does this not just for constant sounds, but also for impulsive sounds. Now, this has not happened to me at an actual measurement. But it is kind of analogous to what happens to distortion. If you have clipping distortion, that is a momentary disturbance to your sound that's not at the input to the loudspeaker. And so coherence can show you if you have transient distortions in your sound. So the other thing that it shows you is all analyzers have some analysis window. They analyze signals in chunks of time, and if you're in a very reverberant space and that reverberation arrives after your analysis window, then that will reduce your reverberation. If we move to a microphone which is closer, we'll see that the coherence gets better and better as the direct sound becomes louder compared to the reverberant sound. So we've got these three things. There's noise, there's continuous noise, there's impulsive disturbances, and there's reverberation. They can all affect the coherence. And so generally speaking, what you want to do is you want to move your microphone very close to your speaker in order to use the M noise signals, so that you minimize the contribution of extraneous noise and reverberation to your coherence, and then your coherence mainly becomes an indicator of distortion. And we have on the next slide a little chart to help you remember that. One way to think of it is what happens when you have the knob. So if you're trying to find the maximum SPL of the speaker, there's going to be a volume knob somewhere. We specify in the procedure where that is. That's an important thing. And what happens when you increase the playback level? If there's constant noise and you increase your drive signal to the speaker, then you will get increased coherence. Whereas if you're in a reverberant space and you increase your drive level and you keep your microphone at the same distance, then the reverberation will, if the sound level goes up 3 dB, the reverberation also goes up 3 dB. And so then your coherence will be unchanged. And if, on the other hand, you have distortion, and most distortions, with some exceptions, but most distortions will increase as you increase the drive level. That, of course, will result in reduced coherence. And coherence, if you look in textbooks, has many different forms, but the form that we're looking at here on the right, there's G and N is the noise, and then all the things in the denominator are related to the drive level. So as your drive level goes up, that denominator goes up, and the coherence correspondingly goes up. So let's see what we have next.
Okay.
And now I'll hand it over to my colleague Merlin.
Thank you, Roger. So as Roger pointed out, in the absence of actual noise or in the absence of reflections and reverberation or room interaction in general, the only likely candidate that could be held accountable for a loss of coherence is distortion. And that's why distortion is one of the stop conditions in this procedure, as we're about to discover. It is, as Roger pointed out, it is an indicator for distortion. It's not very sensitive, but and also we do not intend to replace tried and tested methods, which are more accurate for measuring distortion and whatnot. But it is a good indicator for distortion. And we can rely on it in the absence of actual noise and reverberation and early reflections. And to prove that point, we wrote a little engineering brief that we presented at the AES in 2019, because coherence is a statistical measure that looks at the correlation between the system's input and output. And it can be determined from quantities that are already produced during the calculation of a transfer function. So here we see again some of those quantities that we already saw in Roger's table just now, and notice that even if you don't speak math, if it's not your second or third language, you might be able to appreciate that some of the symbols that you see to your left, you also see on your right. So we basically get it for free. Now, the problem is that if you measure noise and you look at the band spectrum, let's call it an RTA, at the band spectrum of a noise signal, and you introduce as much as 50% harmonic distortion, that the band spectrum will not change in a significant way. And this is a part of a video that you will find on the MNoise website that to which we showed the link earlier. You can also get there by using the QR code. But not only is this hard to measure using single-ended analysis, with noise signals, it's also notorious hard to hear. So that's not the analysis vehicle that we like to use for these tests. We prefer to use transfer function analysis. And if you were to repeat the experiment using transfer function analysis, now you will see that every time we add distortion by as much as 100%, that without exception, the coherence comes down. So without exception, you see that once you introduce harmonic distortion, that in the absence of actual noise or room interaction, reverberation, early reflections and whatnot, without exception, you see coherence come down once distortion entered the equation. So in that engineering brief, we concluded with the table that you see in front of you. This is a transfer function made with MNoise as the source. And we showed that there's a relationship between a certain amount of THD and the expected loss of coherence, and that ended up becoming one of the stop conditions in the procedure that we're about to see soon. To read more about this, please download a copy from the AES library of the engineering brief in question. Which brings us to the present. So here we see the cover page of the current standard draft, the draft which talks about measuring loudspeaker maximum linear peak SPL using noise, and hopefully, as Roger pointed out, makes it so simple that it is as easy as determining the weight of a loudspeaker, which nobody questions, because surely any respectable manufacturer is capable of accurately determining the weight of a loudspeaker. So here we see the conceptual test. We have a signal generator, which produces the MNoise signal, and then we have a volume knob. And where this volume knob lives is mission critical, because once we increase the drive level, we'll expect to see a change in the shape of the transfer function, in the magnitude response, but also in the coherence. And we want that change in the shape of the transfer function to be a function of the system under test, not of the volume knob. The volume knob might invoke the change, but we do not want the volume knob to be part of what is effectively the transfer function. So it's very important that that volume knob lives upstream and does not become a part of the system under test. And then you will also notice in this diagram that we have two microphones. Now, these don't have to be two microphones. There are circumstances where they could be one and the same microphone, but we have two microphones with two distinct job descriptions. The microphone closest to the system under test only has one job description, which is to detect a change in the transfer function. Now, how much of a change? We're about to discuss that soon, but it's there to detect a change in the transfer function. And that means that for that microphone, it's perfectly fine to live in the near field of the loudspeaker because we're not trying to get a boutique transfer function. We only want to see a relative change in the shape of the transfer function and its coherence. Whereas the sound level meter that is ultimately used to determine the SPL at a given playback level in the interest of a data sheet or other applications, that microphone needs to live in the far field. And the far field is a moving target, if you will. That being said, you can imagine that there might be circumstances, such in an anechoic chamber, where you can have one microphone fulfilling both job descriptions, because even at 4 meters distance, you still have ample signal to noise. There is no reverberation, obviously, so you still meet the conditions to execute this procedure. And before we go on to the next slide, I just want to make sure that me and my co-host agree 100%. Roger, is there anything that you would like to add at this point?
No, that's good. This, the videos that exist already talk about where this playback level should go and how to cable things together. So you don't have to rely on this particular presentation to get this part right.
Excellent. Well, with that being said, let's look at the conceptual procedure. So we're going to start by playing back our M-noise wave file at a relatively low level where we're confident that the loudspeaker is still within its linear range of operation. And one could argue that that's a little bit of a judgment call, but surely an audio professional will be capable of finding that ballpark estimate where we can reason that the loudspeaker is still within its linear range of operation. And this is actually something that we can validate, because if we were then to increase the drive level ever so gently, and there is no change in the shape of the transfer function, either in the magnitude response or in its coherence, then we have just proven that the loudspeaker is still within its linear range of operation, where the outstep, the acoustical output follows the electrical input in lockstep. They move in tandem. So that's how you can prove that you're still within the linear range of operation. That being said, if you continue to increase the drive level, then sooner or later, the loudspeaker will no longer be linear. That's to say, the output is no longer capable to follow the input in lockstep. And that will manifest itself as a change in the shape of the transfer function and possibly in the coherence that goes with that transfer function. And then the question becomes, how much of a change is acceptable, and when does it stop to be linear, and when do we enter the nonlinear realm? And again, because we really want to make sure that we get this point across, before we go to the next slide, Roger, anything to add at this point?
No, that's something I do want to emphasize. I'm not going to add, but I'll emphasize. The procedure, the standard is going to be kind of long. We dotted our I's and crossed our T's and got a lot of input from the consensus, even from the community. And even if you look at the procedure as it was originally posted at mnoise.org, it seems a little dense. But really, in essence, it's these 3 steps. Play it at a low level, and then turn it up a little bit and confirm that it's linear, and then keep turning it up until something goes wrong. That's really the essence, and we think that that's a pretty universal thing that can be independently verified.
Thank you, Roger. So that brings us to the stop conditions. There are 3 stop conditions, and once either of them is met, doesn't matter which one comes first, which one comes next, once one of these stop conditions is met, then that's where in English you say that's where the buck stops, right? That's the maximum playback level, and then the follow-up exercise will be to determine the SPL at a preferred listening position. But the first stop condition is 2 compression over at least 2 contiguous octaves. And we had some feedback. People wondered why not 1 dB, why not 3 dB? And hopefully Roger can speak to that.
Well, we did quite a lot of testing internally before we published, before we released M-Noise in the procedure, and we found that it was, in order to reproduce it consistently, if you, we literally left the speaker and the procedure in a room and had different people come in and measure it, and in order to reliably get the same maximum SPL, you had to look for more than a dB of compression. We're used to doing measurements plus or minus a dB. That's a very common error bound. So you need to look for a compression which is larger than that in order to reliably get the same answer each time.
Thank you, Roger. Then the other thing and this is the beauty of the collaboration with the fellow task group members, which is that there were people within the task group that felt that there should be a second stop condition, and this is basically inherited from the AES-2 2012 standard, which has a stop condition which is 3 dB compression anywhere within the system operating range, no matter whether it's broadband or narrowband. Once you have 3 dB of compression anywhere, then the buck stops and you've reached that maximum level. So this is something that we inherited, and we as a task group are happy to adopt that stop condition from existing standard work. And then finally, we're not only interested in compression or possibly even limiting, we also want to look at distortion, and that's where coherence enters the equation. So the third stop condition is that once the coherence drops below 91% over a frequency span in excess of 1/3 octave, anywhere within the system operating range, that's another red flag, that's another criterion to stop increasing the drive level and start documenting the SPL. Now, 91% might be a little bit elusive, but you can also think of 91% as a signal to distortion power ratio. So when we talk about 91%, we're effectively saying that by the time your coherence drops to 91%, our signal power only lives 10 dB above our distortion power, and surely things have become nonlinear, and we should stop increasing the drive level. So once any of those 3 conditions are met, it's game over, red flags have gone up, and it's time to document the SPL level. And some of these subconditions were already present in the existing work that Meyerson did, but some stop conditions were augmented during the further development within the task group, which brings us to this little intermediate slide about building consensus. The beauty of doing this with a task group is that you really, get to cross T's and dot I's. And there were many topics that we discussed at great length, such as the derivation of the test signal. And are we allowed to use filtering or not? And is this procedure or is this standard only intended for finished products that are ready to go to market? Or can it also be used for component testing or transducer testing? And all of that has been discussed at great length. The stop conditions have been carefully reviewed, which led to the addition of the 3 dB stop criterion. And coherence as an indicator for distortion has been discussed at great length. Because if we're going to rate nonlinear behavior, what is the vehicle that we're going to use to that purpose? And even frequency weighting has been discussed recently at great length, because are we going to publish Z-weighted values? Are we going to publish A-weighted values, or both? Which shall be mandatory, which are optional, and whatnot? All of that has been captured in the standard draft language. And again, hats off, big shout out to the task group members, because there were really some pickles. And we resolved these issues by resorting to surveys. We would send out surveys using tried and tested means, and we would have voting procedures, including voter guides. We would have people draft language for a pro, and we would have people draft language in favor of a con. And all of that went into, at times, reaching consensus and resolving differences of opinion. But in the end, we came through, and we're making great progress. Roger, before we go on, do you have to add something from your point of view as co-chair?
Yeah, well, like you, I'm grateful for people. This started very close to the beginning of COVID, and we've had people very dedicated to this the entire time. Our personal lives were changing quite drastically while we were plugging along at this. I will point out that we've had this input that we've had. I think is very important, and it covers a lot of the edge cases. But the essence is still there. So if people want to get a quick start and try this, they can go to mnoise.org and get the signal in the original procedure, and they can get some experience with it. And the essence of it remains unchanged.
Thank you, Roger. So with the stop conditions in place, we can now bring things together, and basically the entire procedure is a two-step process. The first step is simply going to be determine the maximum playback level until either of those three stop conditions are met. So just keep increasing the drive level, turn up that volume knob until you either see 2 dB compression over at least 2 contiguous octaves, or at least 3 dB of compression anywhere within the system frequency range. And finally, stop increasing the level once coherence drops below 91%, i.e. your signal and noise power are now within 10 dB of each other, which is clearly nonlinear. That's the first part of it. And once you've determined that maximum playback level, all that's left to do is to recall that level and now determine the SPL at a preferred listening position. And that could be, in the interest of a datasheet, this could be 4 meter in an anechoic chamber, and then reference back to 1 meter. But it could also be used just as well for validating the performance of a commissioned loudspeaker system. So maybe there was a tender that requested XYZ dB at the front of house position and for music as the source, and now you want to validate whether that system is capable of delivering that requested SPL, and then you could use the same procedure. You just recall the maximum playback level, which you've documented, and now you're going to measure the SPL at the front of house position to see whether you can hit the requested level. So there's a lot of ways to use this to our advantage. And we're going to show you some video clips that basically show this in action, starting with a small studio monitor. So the process goes as followed. The first thing that we're going to do is we're going to start with a preliminary playback level, where we're confident that the loudspeaker is still within its linear range of operation. And we're going to verify that by increasing the drive level by 3 dB. And if the transfer function doesn't change after doing so, then we've validated that it's within its linear range. We're going to capture a trace, and we're going to give it a 2 dB offset, and that then becomes the compression target curve. Because what we're now going to do is increase the level even further until we see a change in the shape of the active measurement shown in black in the video in front of you. And notice that its shape is starting to change, and it's almost about to touch the red target compression curve, telling us that we're looking at 2 dB of compression over 2 contiguous octaves. So I'm sure that went really fast. So let's loop through this a second time. We do that for 5 minutes, and then after 5 minutes, we're going to capture the SPL at a preferred listening position. Why 5 minutes? Because due to thermal, things might change, compression might worsen, in which case it's rinse and repeat. The other thing is, of course, that we need to validate the crash factor after these 5 minutes. Is it, comfortably within reach of the expected crash factor of M noise, which for its full spectrum, all frequencies included, is about 17.5 dB. So let's do that once more. We start at a low level where we're confident that the loudspeaker is linear. We increase the level by 3 dB. If there's no change in the transfer function, the shape of the transfer function, we're going to capture that. We're going to give it a 2 dB offset, which becomes the compression curve, the target compression curve. And then we're going to increase the drive level even further, paying attention to coherence, paying attention to the active transfer function, and see whether there's a change in their shape. And once we see that change in their shape, we need to be mindful of the stop conditions. So here we're looking at an example where we see no meaningful change in the coherence, but we do see a meaningful change in the live measurement. So this is an example where compression is the stop condition, which is met first. And then we wait for 5 minutes, and if there's no change, if it's a status quo after 5 minutes, we can capture the SPL at a preferred listening position, and otherwise it is rinse and repeat. So before we go to the next example of a loudspeaker where we see coherence cave first, I want to make sure that we covered all bases. So Roger, before you continue, anything you would like to add?
No, in the interest of time, I think we should keep moving. I do see quite a lot of questions in the Q&A.
Okay. So let's look at an example. Right. So let's look at an example of a distorted loudspeaker. Here we start again at a low level, and we start to increase the drive level, but rather than seeing a change in the active transfer function, we start to see that there comes a point where coherence occasionally starts to sag below 91%, indicated by the blue line, which is an indicator for distortion. So in compliance with this standard, by the time coherence sags below 91% for more than 1/3 octave, you've met one out of those 3 stop conditions, and you should document the SPL at the preferred listening position. Notice that in this example, it does not. This system under test is not capable of preserving the full spectrum crest factor of M noise, which is 17.5 dB and change. We've lost 2.5 decibels of crest factor. So in compliance with the standard, this is where you would stop increasing the drive level. Notice that there's no appreciable change in the shape of the magnitude response. However, if we choose to ignore coherence, i.e. distortion, and were to focus only on a change in the magnitude response, we would need to increase the drive level even further. Now we see 2 dB of compression over 2 contiguous octaves, but notice also that the entire high frequency section is showing signs of distortion about 3K15 and whatnot. So then after 5 minutes, if there is no appreciable change in the shape of these transfer functions, we would document the SPL. And the 2 examples that we showed here are loudspeakers that are in the same ballpark. And now you see the problem that this standard is trying to resolve, which is that triple-digit metric in the datasheet does not reveal how the loudspeaker sounds by the time that you get to that level, by the time you attain that level. And that is, of course, something that is worth improving. Is the loudspeaker still sounding acceptable by the time you reach that data sheet value or not? And for that, you need to include distortion into your stop metrics, in your stop conditions, besides compression. So all of this work has been really rewarding to a point that we start to see a ripple effect. So other standard bodies have shown a tangential interest in the application of such a test signal. And we even have a SEMT liaison within our organization. SEMT has a B-chain characteristic and expectation working group, and it's looking into the in situ application of this signal to validate performance of systems in post-production facilities and whatnot. Meanwhile, another standard body, which is AVIXA, is also considering the inclusion of M noise in validating the end-to-end transmission quality throughout the entire signal chain. So what goes on in the signal chain completely from source till receiver. And all of that can be achieved with collaborating standard bodies and standard development in general. Which brings us to the forecast. Where are we with the development of this standard? Well, I'm pleased to tell you, Roger and I are pleased to tell you that we're ready to push this standard to the parent committee. So we are SC-04-03-A and we report to SC-04-03, and we're going to push the standard draft to the parent committee. They're going to take it under review, and then they will have an internal call for comments. And if everything goes the way, of course, we hope it does, then that will not take too long. And then it's up to the parent committee to announce a public call, quote unquote public within the AES, but to do a public call for comments. And if that is also blessed by those people that report in, then the AES will move on to publishing the standard. Now, Bruce Olson, I just want to make sure that I did not forget anything at this point.
No, that's good, Merlin. That's once we get the public call for comments, we will resolve those comments, and then the standard will be published. I might note at this point that there's a question about will certain measurement instrumentation manufacturers be implementing this? We do expect that, as many of those companies have members of this task group and other task groups, and typically would then be implementing the standard once it's been published.
Thank you, Bruce. Okay, so this is an exercise in gaining attention and gaining traction for the development of standards. So by all means, join the conversation. If you're interested in this particular standard development, the time has come to join the parent committee. And in order to do so, please contact the standard manager, which can be reached through this QR code. If you do not know who the standards manager is, it's Richard Cabot. If you want to join the parent committee, that's the way how you can join this conversation. But we would also like to raise your attention for AES standards in general. If you go to aes.org/standards, you will learn everything there's to know about AES standard development and more. And that brings us to the official part of our presentation. Before we go to Q&A, Roger, do you have anything to add at this point, or any of the other speakers today?
No, there's some good questions in the Q&A, and I've been typing some answers as I can, but some of them I think deserve a little, well, they all deserve a good consideration, but there's so many, I tried to type as many answers as I could. Okay,
well, we'll do the best of our, we'll try to do this to the best of our ability. You have had a major head start in monitoring the QA. So why don't you take the lead on doing so, and then we'll try to catch up.
Roger, I think I could jump in on a couple of these. So we've got a question about only max SPL for music can be established by this standard, not any other arbitrary signal. And what, from my perspective, what I see happening is that we may well want to develop a companion standard that, for example, looks at maximum SPL of speech. And we would need to go through the same sort of a process as we've done here, but it would be quite a bit quicker because we already understand what the requirements are going to be. So I would say that this one is intended for the kinds of signals that are represented by the corpus that develop the M noise, and that we might then do this in a similar way for other signals. Roger?
Yeah, that's in our SMPTE paper. You know, what I showed in the presentation today was the music corpus, but there was also a speech corpus, and the speech, the RMS level does roll off with frequency more in speech, but the crest factor does increase with frequency without exception, just like music. So yeah, that could potentially be a very quick thing, and you might even think of M noise as sort of a conservative, as it exists right now, is maybe conservative for speech. If you can reproduce a certain SPL with M noise, then you will most certainly be able to also reach it with speech.
That's exactly.
And there's also analysis of cinema, and there's also, you know, it is different, but not categorically different.
Right, and the point is that for some, especially sports facilities, they're interested in pretty high speech levels, and so the fact that speech has a limited bandwidth as compared to music would be a reason for, in particular, for doing that. But if we're really in the domain, I mean, you've got classical music in the corpus, you've got popular music, you've even got some EDM, I think. And so for general music signals or broadband signals, then M noise is going to be pretty close to the right answer.
I'm still ingesting all the all the wonderful
So
questions.
there have been some questions about coherence and analyzers, and what I can say about that is that we have made efforts to make sure that there are multiple analyzers that can perform this test. As a standard, since this is a meeting about a standard, I don't feel like I can make a recommendation. But we've made efforts to make sure that there are multiple analyzers that can perform this step, and I hope that there's more.
And I would expect that those measurement analyzer companies would then create their own white papers that describe how you might use their analyzer to do exactly this test. So we know ones that work internally in the committee. We're not going to comment on those, but certainly it's been developed so that a wide range of measurement tools can be used to do this measurement.
Yeah, that's the nice thing about having a standard is then people can refer to it to make sure you can do interchangeable measurements with one measurement device versus another.
I don't want to cherry pick any questions, but there are just so many. So there are maybe some things that we can relate to because they've been captured in the standard. So I'm just gonna. There's a question by Ralph Kassler. Is it on purpose that the integrated loudness of the M noise signal is exactly minus 23 LUFS or loudness units full scale? I don't think that that's a coincidence. I mean, that value might be consistent, but that it's close to that value is not a coincidence because that has to do with SMPTE compliance. Roger, can you speak to that?
Yeah, so it's morning here in California, so the exact number of the SMPTE standard escapes me. Is it 2092? SMPTE has a standard
2095-1.
-1, right? Okay, so SMPTE has a standard for pink noise, which prescribes a particular RMS level, and M noise has the same RMS level. And that means that it's not peak normalized. There is not a 0 dB FS, 0 dB OV sample in M noise. It's a couple dB down from that. And the RMS level is the same as is specified in the SMPTE standard. So that it was not on purpose that we picked a particular level in loudness units, but that might be a consequence of being compatible with the SMPTE standard.
Thank you, Roger. Now, Bruce, I hope we're going to capture these questions so that we might be able to address those offline one way or another, because they're excellent questions and also very interesting to us as a task group. I'm just not sure that we will be able to answer all of those within the time given. I want to take another question, which is also addressed in the standard, which is a question by Scott Orth, who's asking: the spectrum of M noise appears to follow the average spectrum of music at high frequencies, but ignores the roll-off on the low frequencies. Why is that? And I think Roger can speak to that.
I'm sorry, I was distracted by reading some of the other questions.
Yes. So the spectrum of M noise appears to follow the average spectrum of music. This is a question by Scott Orth at high frequencies, but ignores the roll-off at low frequencies. Why is that? So why does M noise go down to 10 hertz?
Well, that is what came out of our analysis, that there is content down there, and yeah, some content starts at 40 or 80 hertz, doesn't have much below, but other content goes all the way down to 10. And when it does, it tends to have a crest factor of about 12 dB. So our thought was, okay, well, let's put energy in M noise, all the way down to 10 hertz. 10 hertz is, again, from that SMPTE standard. With the crest factor, if there's going to be content down there, we know about what the crest factor is going to be. So let's put that content in M noise. And then if people don't want to use that, then they can high pass it at a higher frequency. And that is a part of the standard. We had discussions about that. That's one of the polls that Merlin put effort into making. And it was decided that we want to allow high passing, but we still want to have some chance of having apples to apples comparisons, and so there are suggestions for what frequencies you should use for high passing if you do it.
Right. Thank you. I'm going to take a stab at another question by Ralph Kessler. What is your exact definition for crest factor? He did a field measurement, and the field measurement said that the peak lives at -3.5, whereas the RMS lives at -18.5. And if you subtract those numbers from each other, one might come to the conclusion that the crest factor is only 15 dB. But that has more to do with the fact that is your RMS value shown in compliance with AES, which would be AES 17, top of my head. Is it AES, is it dB full scale, or is it in compliance with the ITU standard, which is dBOV? Because that same RMS level in dBOV would read -21.5 dB, in which case, if you subtract the numbers, you would end up getting 18 dB, which is the full spectrum crest factor of M noise. So when you meter this, you need to know what the RMS, with which standard the RMS level is compliant in your meter. But the crest factor is literally the classic textbook definition of peak to average ratio, the peak to RMS ratio. So I hope that answers your question, and if not, please let us know. Now, at our Colleen or Bruce, how long are we expected to go on? I mean, I'm not going anywhere, but just in the interest of managing questions.
We could go a little bit longer. It's not, we don't have to stop exactly at 10.
Okay. Roger, have you seen something that you feel comfortable questioning at this point?
So there's a question about whether a dual channel analyzer is required or not. And it is. To be compliant with the standard, you do have to use a 2-channel analyzer. But you will see, if you just use a sound level meter, you could possibly see this. As you turn the level up 2 dB, you should see the SPL go up 2 dB every time, and eventually that will stop. And if there's distortion, especially clipping distortion, then you'll eventually see the crest factor reduce. Now you can't do a standards compliant measurement that way, but you can see what's going on. Although you have to rely on whatever device it is that you're measuring. You have to rely on the manufacturer stating, what's the maximum signal it can handle without being damaged. And that's, that's not necessarily the case right now. I don't think you can always have confidence that you can play any signal at the level prescribed in a data sheet and the device won't be damaged. So it's a place that we want to get to. And so hopefully manufacturers will see this standard getting published and see, people are going to do this measurement, we better accurately state what our speakers can handle, so that when people try to test this independently, they'll get the results they expect, and the speaker will continue to function correctly.
Excellent. Thank you, Roger. I'm going to take a chance at answering a question by Justice Verhagen. He is asking, how does coherence include intermodulation as well as harmonic distortion? So please allow me to defer you to the engineering brief that we wrote on the topic. And that engineering brief also makes reference to other AES papers by industry veterans. Using coherence as an indicator for distortion is by no means novel, and all those phenomena are taken into account. Coherence will show you intermodulation distortion as well as harmonic distortion. And then there's another.
Let me answer a couple of questions that are towards the end here. Have any test equipment vendors committed? Is there any traction for consumer or automotive products? Both of those, there are manufacturers, because this is a manual test, that is, the stop conditions require an operator. This is not an automated test, so it is a manual test. That's how it's written. So it can be implemented on any device that's capable of reading those stop conditions. With regard to consumer or automotive products, we have a Class A liaison with IEC, and once this standard has been published here, we know that there's interest from the IEC in what we're doing, and it would be very likely that we would move that forward towards an IEC standard, which generally covers consumer or automotive products. We also, through that liaison, have a liaison with CTA. So once it's we've published it as a standard, then we would see it being implemented by others. And then Joe Bruzzi asked about does this apply to a band limited device? Merlin, you'd already spoken to that a little bit earlier.
Yep. So the spirit of the standard, and that should make sense. The spirit of the standard is that with the publication of the data comes the burden to disclose enough information such that an audio professional with access to the same equipment can reproduce the results. So yes, you can use filters within constraints for transducer component testing and whatnot, but if you use those filters, you have to disclose which filters were used, what their alignment was, what the corner frequencies are, so that another user, another audio professional can achieve access to the same equipment, recall all those settings, and validate your claim. And that is a spirit that hopefully everyone on the call can appreciate. To the point of automotive and consumer electronics, yes, we're happy to inform you that on the task group there are members that represent the automotive and the consumer electronics. And the other thing is because we can also do this transfer function in post. This is one of the things that we discussed. Where's the ingress point in a wireless Bluetooth loudspeaker? Where do you inject your signal? Well, you could play it back from a USB key and then, record the output with a microphone and do the comparison, do the transfer function in post. So there's also ways to apply it in that fashion. You don't literally need to have a hardwired connection into the device and their test. There's many ways how this could be used. So there was one question by John Neumann. I'm trying to, maybe it's already been answered. Lon Neumann, which is the
modulation.
Yeah, does the detection of threshold of distortion take into account the threshold of human perception? Is that factored in? And I like to speak to that. Like, for me, it's the difference between lossy compression and lossless compression. This is not an exercise in what is acceptable lossy compression. We're not trying to decide whether JPEG is still acceptable or not. This is an exercise in coming up with the penultimate result, which is what is the maximum performance of a system under test under linear conditions. And we all understand that you can push that envelope and possibly reach higher numbers in exchange for some degree of distortion, which might be acceptable to you, but not somebody else, in which case it becomes an exercise in what is acceptable lossy compression, if we make the comparison to photo, such as JPEG and PNGs and whatnot, and what is unacceptable. But that's not the impetus for this standard. The impetus for this standard is to give you a linear performance metrics per metric, which you can then exceed at your own discretion in exchange for a degree of nonlinear behavior, which might be agreeable to you or not. So that's something that I just felt the need to point out.
So there's a question about extreme cases of music recordings, and there is in the SMPTE paper there's a list of music styles that we analyzed, and we did analyze multiple tracks from different genres and from different decades. There's a list of all the types that were analyzed, and we did make an effort to not just look for something typical, but look for extreme cases. And there were cases of extremely compressed recordings where just the raw recording, the full bandwidth recording, had a very low overall crest factor. So those were included.
Yeah, and it even more. We did not only look at pre-produced recordings. We also actually looked at board mixes of sounds captured during actual concerts, which one can imagine are maybe processed in a different way as you would do for something as recorded production or produced recording. So we really try to cover all the bases or all the obvious expectations. So with that, yeah, Roger, you wanted to say something?
Sure. Well, just quickly, there was a question about group delay and longer group delay, and my answer would be, as long as your group delay is within the analysis time of your analyzer, then you will have high coherence, and that won't matter. And there's a certain brand of loudspeakers that I have worked with the most in my career, and I've never seen one that had a group delay which was longer than the analyzer. Merlin has a wider experience. Maybe you can talk to that, but I think that would be unusual for a speaker to have a group delay so long it would be outside your analysis time.
Yeah, you would really need a gratuitous amount of phase shift, i.e. group delay, to start it, affect the coherence as a function of bias, as it's known. It's in the interest of this exercise, the bias that group delay might introduce is negligible in light of the time records that are typically used for doing this kind of analysis. So our host said maybe we can push till 15 minutes over top of the hour, which leaves us with 1 more minute. I just would like to use the opportunity to just thank my fellow task group members, our fellow task group member once more, who've been doing a great job during a pandemic, which I do not take for granted, given the challenge that we're facing at the time. So thank you very much. Also, once more, Colleen, Bruce, Richard, and Steve, thank you for this opportunity to present our work. And maybe, Bruce, do you want to make an announcement over the next webinars that are in the pipeline on the topic?
Actually, I'll let Rich do that. He knows better what's coming.
Rich, are you in a position to disclose some information about the other?
Our next webinar is going to be on AES 67 over wideband networks, essentially putting AES 67 on the internet, which should be a really good webinar. And that's work being done by SC-04-03-A, and that's in 2 months from today. And then the one after that will be on analog audio interconnects, problems with grounding and shielding, and work that's being done in the SC-05-05 group to develop a standard way of specifying what interfaces are on products so that you know when you're designing a system using products from different manufacturers, you have a better idea of whether they're going to work together. The data sheet will give you the information you need to understand how it's going to fit into your system, those kinds of things. So that's the next two standards coming up, next two webinars coming up.
Excellent. Well, we'll capture these questions and we'll address them within the task group and make an attempt at answering them offline one way or another. But as always, we've run out of time.
Thank you both for a great presentation.
Thank you for the opportunity.
Thank you very much for having us.
Thank you, Marilyn and Roger. With that, we'll close the webinar.
Bye-bye.